All right, we still have a few people joining, but I think we'll get started. My name is Trey Avery, and I'll be leading the webinar today. I just wanted to kick things off by introducing the CEO of Magstim EGI to welcome you to the webinar today.
Thanks, Trey. Hello, everyone. Thank you for joining the Magstim EGI webinar today. Thank you so much, Trey and Dr. Sarah McCormick, for graciously sharing your insights and expertise with us. My name is Ronnie Stallacampo. I'm the CEO for Magstim EGI and the Welcony Group. We have some great news today about 2 new technologies to accelerate your neuroscience research. In fact, we developed these technologies that you'll see today because neuroscience leaders like you requested the tools to enable them to better study and treat the brain. We always want to hear from you. Please reach out, share your successes, no failures, research developments, and any needs you may have. Your knowledge and research endeavors drive and inspire us. Be sure to look for new innovations from Magstim and EGI in the coming months. Our R&D teams have a very, very busy 2024 planned. At the end of the session today, there will be a brief Q&A monitored by John Leadham. Please use the chat feature to ask any questions. Before we start, I need to read a brief statement to make our attorneys happy. Scientific content remains the intellectual property of the authors. This webinar is sponsored and organized by Magstim EGI. However, Magstim EGI does not engage in generating or editing scientific content presented. Inclusion in this webinar should not be taken as an endorsement of the scientific findings by Magstim EGI. Please note the use of Magstim devices or EGI devices for other than the FDA cleared intended use is considered investigational. Now, I have the pleasure of introducing my colleague, Dr. Trey Avery, who holds a PhD in biobehavioral sciences from Columbia, where he managed a dense array EEG lab. When I joined Welcony about 2 years ago, Trey provided me with a fantastic overview of EEG and just how important dense array is. So I know you'll enjoy his talk today and Dr. McCormick's talk. With that, I turn it back to you, Dr. Avery. Thank you.
Thanks, Ronnie. We will get started, and just to make sure that we can, you can see all the content in the slides, we're gonna turn off my camera for the slide portion, and then we'll turn cameras back on for the 2 Q&A sessions. We'll have one following the TMS section, and then one following the EEG section. Great. All right, so we're going to talk about some new products that we'll be making available starting today. One of the things I'm most excited about today's launch is that we're presenting data for each of the new products to really show you what they're capable of. And as a former researcher, I think that's really important to really show you, data when it comes to the effectiveness of products. So that's going to be an exciting part of today's launch. We'll start with new options for TMS and high-density EEG integration and data collection and analysis. And then we'll be introducing a modified version of our sensor net that's designed to work with more types of hair and expand inclusion in neuroscience research and clinical care. And at the end, we'll be sharing data from a site that's been using these new tall sensor nets, and as well as our standard sensor nets to show you the benefits of this new optimization. So the Magstim EGI geodesic EEG system is designed to grow and evolve as your research expands. So often you can go into a whole new area of research simply by connecting a different style sensor net or combining our system with another modality. So today we'll be announcing improvements to a few spokes in this wheel with the goal of making the effort to advance neuroscience research a bit easier with new integrations and enhancements to our technologies. So the combination of TMS and EEG offers endless potential in terms of studying the effects of TMS on the brain by recording EEG during and after TMS. I really think that TMS is underutilized by EEG researchers as it allows researchers to interact with brain areas in relation to experiments to test interactions between nodes in a brain network, as well as as what we'll show today. Um, it's going to get easier to time lock TMS to brain states in experimental protocols, and then be able to analyze the EEG data as a result of that. So many of you are probably familiar with some of the equipment on the screen. So on the left, we have the geodesic EEG system, available in a range of channels from 32 to 256, saline, gel, or paste-based sensor nets, just depending on how long you need to record. And the saline-based sensor nets can be applied in about 5 to 10 minutes. So it's a significant advantage, particularly if you're working with sensitive populations, or you're just interested in taking up less participant time and being able to kind of send them on their way without gel in their hair afterwards. On the right-hand side of the screen, we have Magstim TMS stimulators. So the Bistim 200 or the Rapid. They come in different configurations as they are designed for different types of TMS pulses, depending on what you're trying to do. So some are optimized for repeated fast pulse trains for, say, clinical therapies, or some are designed for single monophasic pulses or biphasic pulses, depending on how you're trying to interact with the brain. At the bottom here, we have the TMS interface module, which is just a handy little box that connects to the back of the TMS stimulator. And that is the beginning point where some of the integration work that we've been working on and we'll be releasing today allows you to connect with the geodesic EEG system or have other hardware initiate TMS pulses based on, say, a time-locked experiment or other factors. So today we're just making it easier for these all these pieces of equipment on the screen to work together. And we have two options for collecting high-density EEG with TMS. So for a very long time, our main recommendation was the microcell GSN. So that sensor net has a low electrode profile, allowing you to get closer to the scalp for TMS, which is often seen as a benefit. The challenge with this is that it does require gel under each electrode, and some skin prep is required, and so it takes a bit of time to prepare. The recovery time of the TMS from the TMS pulse is not ideal, with about 40 milliseconds. So if you're doing TMS EEG together, it can take a little bit of a toll on some of those early components many EEG researchers want to look at. But maybe the biggest challenge, and it's really the focus of today's webinar, is that this low-profile electrode was difficult to use with many hair types. So dense, textured, curly hair can sometimes lift an electrode off the scalp and make it difficult for you to collect high-quality EEG data. So we started looking for an option that would be optimized on a number of these levels. And what we found was our sensor net that we currently use for MRI is actually ideal in a lot of ways for data collection with TMS. So as I was discussing before, it can be used with saline, gel, or paste, depending on how long you need to record. No skin prep is required. And if you're using saline, as many users of this net are, it can be applied in about 5 to 10 minutes. And afterwards, there is no residue other than salt left in the hair. So you can send people on their way much more quickly. The electrode profile is taller, and so it does require about a 10% increase in TMS power. So, we acknowledge that there's going to be certain use cases where this isn't an option if you're already at the maximum TMS output. But the balance of other benefits here in terms of a faster recovery time, cutting that recovery time down down to about 10 or 15 milliseconds, which will be showing data that we collected in a little bit. And also that you can use it with more hair types, and you can use it both in MRI with TMS or just for standard EEG. So it's a very versatile sensor net, and that can be really ideal for multimodal labs. So on this next screen, we have our kind of engineering diagram to just show how these things are connected. And don't worry, if you're interested in pursuing this, we have documentation about how to get all these things connected, and you can work with our team to ensure that you have everything you need. We also have a support team that can help connect this on site when they're installing equipment. So next, I'll just show you a short video demonstrating what we're talking about in terms of this integration. So you can see here that we have the net connected to the amplifier and NetStation software streaming. And you can see each time there is a TMS pulse, you get an event marker, and that is recorded in the EEG software. So for many researchers, it seems like, a TMS pulse is huge and you should be able to easily identify it, but many software programs that do TMS EEG require a event onset to know exactly when it happened so that you can easily analyze your data. So this just adds a little bit of more functionality on the EEG side of TMS EEG. And the next thing, I'll start by discussing the elephant in the room, which is, yes, this product looks like the emoji I use most on my phone, but it's a helpful little gadget that makes time-locked TMS EEG much easier, allowing you to pair TMS pulses with audiovisual stimuli in E-Prime. So E-Prime is a software program that allows you to present AV stimuli. So to a person sitting in a chair, they can see pictures or video or audio. And then we get time-locked responses in the EEG stream. And similarly with this device, the Chronos extension or Chronos adapter for TMS EEG, you can now tell E-Prime to fire a TMS pulse in relation to specific things you would be showing a participant or a patient. So this is an example of this could be in addiction research, where researchers are showing pictures of, say, an addictive substance, and then pairing it with a TMS pulse to stimulate brain areas related to addiction or other conditions of interest. Again, here's our similar diagram, which seems a little bit more complicated, but as I was saying before, we have lots of documentation to get you all set up and a support team to help you along the way. And as before, we'll show a quick video to demonstrate what we're talking about here. So you can see that the E-Prime computer is on the left, and it says that the pulse is resting and the pulse is firing. And each time that happens, we're getting an event marker in the EEG software. So it seems fairly basic, but can be an important step to make any time-locked TMS EEG research much easier for people that don't have a team of grad students or postdocs that can do a bunch of coding. This makes that whole process a bit easier to do. And as I was saying before, we recently tested the performance of the hydrocell MRNet with both biphasic and monophasic TMS pulses and processed the data with the open source Tessa toolbox. It's a MATLAB-based toolbox. And you can see there are slightly different amounts of data removed depending on pulse type, but you can clearly see many of the most commonly studied TMS EEG components. And remember, this is using a sensor net that allows you to apply 256 or less electrodes very rapidly, so you can study the full resolution and complexity of these brain responses without sacrificing a ton of lab or participant or patient time. And it also works with a wider range of hairstyles, which is very important. So we think that this hydrocell MRNet is a nice addition to the TMS EEG profile product portfolio, as it allows you to collect data with more people that would not be really compatible with the microcell net or cap-based traditional EEG systems. And again, since the net can be easily removed, put on or removed, some groups are doing just pre-post TMS, some groups are doing all the way through pre, during, and post. It's really up to you, and really, I think this new option just gives you more flexibility in this area. We had 2 webinars on TMS EEG related topics in 2023. So one covers the TESSA workflow that I just showed data from. So if you're interested in that and how that data analysis occurred, you can view that webinar. And then we also have more on the application side of things, where Jamie McPartland from Yale talks about his work in high density EEG biomarkers and how he's using TMS to study how that biomarker is affected with treatment such as TMS. And those webinars are available on our homepage, EGI.com, as well as YouTube channel. So if you wanted to analyze your data in an open source tool like TESSA, we have a plugin called MFF, which is our file format, MFF MATLAB IO. So this is available in the EEG Lab plugin library. It was recently updated to, we're now in version 4.1. It was developed by Arnaud Delorme, one of the founders and leads behind EEG Lab. And this is a great tool because it allows you to easily bring your data with no exporting directly into MATLAB or Python-based toolboxes. It also allows you to export your data back to NetStation for better visualization of high-density EEG. Not all open source tools are really optimized for 256 or that many channels. So this tool allows you to bring your data out of our software into open source tools, back into our software, and if you want, or export it to a format like BIDS, which is increasingly popular among journals and funders that want to make data publicly available in a common format, so that basically someone can pick up a data file and know exactly what was recorded, be able to kind of understand the data, and possibly reanalyze the data in a different way. So lots of flexibility there, and the GitHub page listed at the top there is where you can find all the documentation about the plugin. And also, if you encounter any bugs or have a feature request, those can be submitted to the developer in that page. We also feed forward from our support team any bugs or feature requests, and they're actively managed and supported in an ongoing basis. So great tool to use if you're not using that already. And then we also have a new, or I should say, a renewed partnership with BISA. So many people, if you were a long-term user of EGI or other EEG systems, have probably encountered BISA software in your travels or conferences, and it's a great GUI-based software that allows you to do really complex analyses of your data. So one of the reasons we reestablished this partnership is that one of the challenges of many packages was that it didn't really allow you to explore the full complexity of high-density EEG data. And with BISA 7.1, their newest release, there's great connectivity and source coherence features that you can really look at the relationships of brain data across the brain. So, we're really getting to the point where, kind of like with the early days of fMRI, where, you would highlight a very small voxel that is producing some response to some scenario. And really, EEG is really in the same path, where now we are starting to look at dynamics across the brain. And BISA is a great way of allowing you to explore your data in a more complex way. while not having to do a ton of programming. And they also do have connections with, allowing you to customize certain things. So if you do want to alter things, they do allow you to do some of that. And you can purchase BISA along with other EEG products from us, or on its own. And a new model they have allows you to spread the cost of software across years of a grant or just across years of your lab budget. So it reduces the upfront burden of having to make an upfront purchase all at once. You can use it for a subscription model across multiple years. So lots of great opportunities to analyze your data and to collect TMS EEG data together now. And with that, I'm just going to open the floor for any TMS EEG related questions. So I think John will be joining us to let us know if any questions came up on the chat, or you can let us know now.
Thanks for the excellent presentation, Trey. That was fantastic. It's exciting that we can now add the TMS modality to the high density EEG. I think this is a nice step forward for all of our products, and people can come and source all their products with one company at this point in time, which is exciting as well. We did have a question come in. The first question that came in was, is there other experimental design software that is supported apart from ePrime at this point in time?
Yes, there is. That's a very good question. So the TMS interface module is essentially, so the Chronos box that I showed is essentially generating a TTL pulse, which is a standard communication triggering method across lots of devices. So the Chronos option is helpful in that it's increasingly difficult to find computers with parallel ports as computers are getting smaller and smaller and smaller. And so the Chronos box essentially enables a simple to use parallel TTL generator. But that being said, if you have a computer or another method of generating TTL pulses, you can get the same effect and then use the same integration that would allow you to get events both into your EEG signal when the TMS pulses happen, as well as to trigger the TMS device based on a time-locked event of interest.
Great, thank you. One more question here. How is the TMS-induced noise removed from the EEG recordings?
Yes, that's a good question. So it's a complicated question. So there can be a lot of factors that can induce noise related to TMS into EEG. So as most of you know, it's a large magnetic field, right? That requires substantial power, and having these devices right next to each other could make it could induce some fairly strong noise. One of the ways that we prevent this is by not placing the TMS coil directly on the EEG sensors. So there's different ways, either arms or there's an open source spacer that goes in between the TMS coil and the EEG electrodes to prevent touching. So that's one of the ways that people reduce noise. The other thing is that the TMS, the MR-related MR conditional sensor net that we're introducing as a new option for EEG and TMS has a 10-foot cable that allows you to keep the participant or patient fairly far away from the actual TMS hardware. So as usual with EEG, it's really just knowing the sensitivity points of the EEG and all of your other equipment and making sure that you just have some proximity in between the sensitive points and any generators. So part of that TESSA workshop that's on the webinar that I mentioned from last year does show some of the processing steps that do remove noise in traditional ways, like notch filters or using a tool like CleanLine to effectively remove some of the external environmental noise from TMS EEG.
Great, thanks, Trey. Do we have time for any more questions, or Are you set to move on to the next?
I think we can do one or two more.
Okay, I've got one left here. Have you seen ICA used with TMS pulse artifacts in EEG, and how effectively?
Yes. So this was one that really stumped me as a researcher, and I think so. This is one of the reasons why I feel like showing data and showing specific workflows to make this happen is so critical for researchers because it's easy for one to think, oh, this TMS artifact in EEG is huge. It's got to be the easiest thing for ICA to pick up and easily remove. And it turns out it's really not quite that simple. And the Tesla toolbox and other TMS EEG tools do use ICA, um, but it wasn't as straightforward as I thought. And so that's the reason why they built it into toolboxes, so that you can have the full range of tools to get the kind of results that we were able to achieve. So it's it is kind of its own analysis field, and that there are kind of norms and best practices that have been established, and most of them built into Tessa and other tools. So I recommend again looking at that webinar and then also digging into some of the peer-reviewed articles about these tools and articles that have actually used them for EEG processing.
Okay. I had a whole flurry of questions come in all at the same time here, so I'm just trying to work through them. Perhaps the last question, and maybe we can answer the other ones offline. What sets the EGI EEG caps apart from other systems and caps?
So you know, we were the first to commercialize high density EEG. We have some great pictures of them being born in garages in Eugene, Oregon, and the basically, it's been a process of refinement over the last 25 plus years of learning from feedback from our customers and tweaking things to ensure that we're getting optimal comfort, since people are using these sensor nets with infants, newborns, premature infants, children with autism, other sensitive populations, and then just in general, you know, over the years, people using them in clinics, in clinical settings. And over that time, we've gathered lots of great feedback that allowed us to refine and improve things. And I feel very confident to be able to say that our sensor nets are the most comfortable saline nets available, and that we're getting consistently high quality data. So, it's really just a matter of, we were, early to this game, and we've refined it over the years to make it into what it is now.
Great. Okay, I think the rest we'll have to answer offline.
Okay.
We'll make sure we get those out to people as quickly as we can.
Great. Thanks, John.
Thank you.
So to begin this next section, I would like to start with sharing a little bit of story from when I started collecting EEG in grad school in New York City many, many years ago. My lab was located in Harlem, a predominantly Black and Latinx neighborhood in Upper Manhattan. And our lab studied populations in New York City public schools and immigrants that were learning to read, and clinical populations that were difficult to recruit and get into the lab. So if they came in, our only option was to try to collect as much data as possible. And in many places at that time, the norm was to exclude participants with hair types that people didn't know how to work with, or ask them to drastically alter their hair if they wanted to participate, which could be costly and burdensome to the participant. So, as we know, traditional methods of EEG require scalp contact with minimal impedance or separation between an electrode and the scalp to access the brain's electrical signal. And this has led to findings and generalizations that do not represent the full diversity of our community and our planet. So fast forward to the present, funders are increasingly expecting demographically representative samples, and many more journals and reviewers are expecting considerably more transparency around characteristics in a study population. And a growing number of institutions, neuroscience researchers are expected to support strategies for diversity, equity, and inclusion for hiring committees, research subjects, and other areas, with the goal of making neuroscience representative of the diverse world our work aims to understand. So a wide range of individuals, groups, institutions, and companies are working to address the history of systemic racial bias in the field of neuroscience due to underrepresentation methodological barriers that have only gained broad attention, unfortunately, in recent years. But we're happy that this conversation is happening. And I will quote a Arika Everett from diversityhealthhub.org article that says that over 7 million Americans require accurate yearly EEG recordings to monitor and diagnose common brain disorders such as epilepsy, stroke, mental health diseases, and brain injuries. However, most current EEG systems are incompatible with natural hair for Black and many other patients, leading to the poor data quality, uncomfortable patient experience, and denied access to participate in research studies. So, I'm guessing many of you are well aware of these discussions and challenges, and we're encouraging you to pursue some of the resources that are now available, both in terms of peer-reviewed articles, popular media articles, and scientific articles, podcasts like Science Versus. This was one of my favorite peer-reviewed articles, just because I love a good punny intro to an article. And also there are groups that like Black in Neuro, as well as the ALBA network, all of which are working to improve our understanding of what diversity, inclusion, and representation means in neuroscience. And we are very excited to be part of this big movement of all of these different groups to try to improve this problem. So one of the ways that we started this work was in a webinar from 2023 that talked about inclusive EEG and this term, it was inclusive in a very broad sense. So not only working with all types of hair, but also working in the homes and other settings where you can find patient populations that may not be able to come into a research lab. So I highly recommend reviewing that, and I'll show you some quick examples from that webinar, but the whole webinar is really just a great resource for learning some of the vocabulary that is needed to work with more hair types and be more inclusive, and also think about the people that you need in your lab to be a really, to do the kind of inclusive research that you want to do. So here are examples of from that webinar of putting these are just our standard sensor nets on several different hair types that allow you to see what that can look like. So in some cases, kind of like what I was saying in my kind of early research days, you may not be able to get all contacts onto the head, but sometimes just seeing examples of how other people have done this are tremendously helpful and may give you the confidence, or at least the initiative, to start looking into this and how to do it in your lab. And so in the case of loose braids and locks, you apply the sensor net, and then you can see in the videos, they actually have two people helping apply the sensor net. And then you begin by removing some of the braids or locks through the holes in the sensor net. This is one way that our sensor nets are different than many other EEG devices, in that it's an open structure that allows you to pull loose hair through the openings in the sensor net. And that allows the electrodes to get deeper and closer down onto the scalp, which gives you better data quality usually. And then here is a very fast TikTok of the same thing, where You apply the sensor net, and then a team pulls the hair through the openings in the sensor net. So Dr. Hudak has published papers on this, and I think it's important to realize that for many research questions, this isn't optional. This is a true necessity to be able to study the populations that we want to study, and also to have our work be representative of the full diversity of human brains that surround us. So sometimes just a relatively small change can make a big difference. Don't get me wrong, launching a new product requires considerable persistence and effort, but we believe it is truly worth it. So Magstim EGI is proud to be part of efforts to address such biases in the field with release of a modified version of our high-density EEG sensor net that's been optimized to work with a wider range of hair types. Our open net structure has proved to be valuable in achieving scalp contact, and multiple research labs, including one you'll be hearing from shortly, have shown that these new sensor nets have new applications and methods that have developed, improved their ability to collect high quality data on more hair types than our standard sensor net. So don't get me wrong, some of the, many labs have gotten away with many years very successfully with our standard net. This new net is designed to be optimized to allow you to collect data, better data quality. And we're incredibly thankful for the labs that have started using this very early on and provided such helpful feedback in allowing us to refine it and improve it into the product that it is today. Just some details on this is that it's the same price as our standard sensor net. In the United States, it's available as an FDA-cleared medical device for clinical use or as a scientific research instrument, just depending on what you're trying to do. Most people are using it for scientific research, but we can talk through that if you are unsure. And then in the rest of the world, we are releasing it as a scientific research instrument for research purposes. And you'll see that here we're listing adult and pediatric sizes, and that the sizing on these sensor nets are a bit different since the taller electrodes result in a smaller internal circumference of the net, so you just have to size slightly differently. And it's available in 32, 64, 128, and 256 channels. And currently in the saline option, but if you have other ways that you want to use us, talk with us, and we'll see what we can do. It is also available in infant sizes, but for the time being, we're releasing this as a kind of standard product in adult and pediatric sizes. The infant nets would be custom products at this time, which that's how everyone that's using them currently has ordered them. It's just a small difference in how they're ordered. So if you're interested at any age or any channel count, just let us know and we'll talk you through the process. And with that, I'd like to kick it off with Dr. Sarah McCormick. Sarah is a postdoctoral and future faculty fellow in the Pine Lab at Northeastern University. Pine Lab is one of those places that I think my employer gets a little nervous I might not come home from when I visit, just because of all the work they do and the great people. And in the background of the picture, you can see this really amazing building that they're in Northeastern. But just a fantastic lab. She received her MS and PhD in psychology and developmental science from the University of Massachusetts Amherst. And prior to that, she was a research study coordinator at the Laboratories of Cognitive Neuroscience at Boston Children's Hospital, which, as many of you know, is one of the biggest research labs when it comes to high-density EEG. So in a great lab now and trained in one of the best places you could be trained in. And Dr. McCormick is broadly interested in how the brain is developing to support social understanding and how individual differences in development and experience impact behavior. So with that, I'm going to pass it over to Dr. McCormick.
Awesome. Thank you so much, Trey. I'm also just going to leave my camera off while I go through these data. That way you can fully see the slides, but I'll turn my camera on when it's time for questions at the end. So I'm very excited to share some of our data with you all today. The data I'll be sharing today is from a collaborative effort between the Plasticity and Neurodevelopment Lab, or the PINE Lab at Northeastern, run by Dr. Laurel Gabbard-Durham, as well as Dr. Kirsty Donald at the University of Cape Town in South Africa. So we were just trying to advance to the next screen. There we go. Perfect. So we were very excited to be able to work with Magstim EGI to test the new net structures out before their official release as part of one of our larger longitudinal studies on infant neurodevelopment, which we call KULA. We were very excited about these net modifications in particular because while we know others are working on solutions to improve inclusivity for adults and older child participants, net placement time and the patience of our infant participants are often have much shorter windows. So the hope was that this modified net structure design would improve data collection and inclusion of infant participants with curly, tightly coiled, and or afro-textured hair without sacrificing net placement efficiency and time to start data collection. So I also want to highlight that this effort was also really led by Nwabisa Malandu, who's a neuropsychologist trained at UCT and was also involved in the KULA project. She just can't be here today because of the time difference, but she's also happy to answer any questions that I can't today over email. Also, a preprint of the data that I'm going to be talking about today will be available in the next few weeks. Okay, so, perfect. So as has been shown already, the modified pedestals are taller and made of a more rigid molded plastic material compared to the shorter infant net pedestals. And at the top right here is just an image of one of the modified tall net structures placed on one of our toddler participants. So to test the effectiveness of these modified net structure designs, we recruited infants from the larger KULA study, which is a longitudinal study on infant neurodevelopment in Cape Town, South Africa. Participants were initially recruited for the larger study from an established pregnancy registry site at Gugulethu Midwife Obstetrics Unit, which is located in Gugulethu, an informal urban settlement in the Cape Town city in South Africa. We ended up with a sample of 35 infants between 6 and 11 months of age. We did test an additional 15 infants, but we excluded them from analyses due to inconsistent net placement between the short and the tall net, or if there was extreme fussiness from the infant for at least one of the recordings. So as a part of the KULA study, infants are already participating in a resting state measure where they watch a silent video for 3 minutes. And I'll just show a short clip of that here. Perfect. Thank you, Trey. So if you're not familiar with how we collect resting state data from infants, this is one way we typically do it, where we'll show them, an engaging but silent video that they'll watch for about 3 minutes. We might use other methods to engage them, such as blowing bubbles or playing with a silent toy otherwise. So we had infants repeat this baseline measure 2 times. The first time they would be wearing the short net. We would then remove the net and repeat the resting state baseline measure with the modified tall net structure design. A widely available leave-in conditioner was applied to infants' heads before the first net placement. We also measured impedances, as we typically do, and saved them out from each of the recordings. And prior to the placement of conditioner, we also measured the hair height. We are broadly calling this in centimeters, where we would just sort of measure where or like how tall the hair height was measuring at rest before we applied any conditioner. So we weren't doing anything else. And we generally measured from the top of the scalp or where the most hair seemed to be present. Data were also processed through HAPPY, which is a processing pipeline optimized for developmental data that's freely available on our lab's website as well. So our main measures of interest included to sort of evaluate the effectiveness of this taller net structure. included looking at the impedance values recorded, prior to the start of each resting state recording for the online reference electrode, as well as an average measure from all of the electrodes included in analyses. We do exclude the outer rim of electrodes from our analyses, which is typical or becoming typical in infant data analysis. We also looked at the percentage of good channels or good electrodes retained for analysis and the percentage of good number of segments retained for analysis as well. And then we compared this all of these measures with hair height measurement to see if the tall nets were doing a particularly good job at retaining data for infants who had taller or greater amounts of hair. So just hop right into data. We do show that there is a significant difference between the nets in the impedances of the online reference electrode, which for us is CZ. The tall nets are showing significantly lower impedances in that online reference electrode compared to the short net. Next, we see a very similar pattern for the average of all electrodes used in analyses, so minus those rim electrodes, where again, the tall net showed significantly lower impedances on average for all electrodes used in analysis. Yes, additionally, we saw a significantly greater percentage of good channels retained for analysis for the tall nets compared to the short nets as well. And finally, for the overall sort of analyses, we do also see that the tall net showed a significantly higher percent of usable segments retained for analysis as well compared to those short nets. And so when we look at these measures compared with hair height, we do see that for infants with greater amounts of hair, the tall nets showed significantly lower impedances for that online reference electrode, whereas the difference between the two nets is not significantly different for infants who had no hair to less than a centimeter of hair when we measured it. And we chose that sort of cutoff measurement because it's approximately the height of the short pedestal. So we were looking at hair heights that were greater than the height of that short pedestal to see if the taller modified pedestals would be more accommodating. And that does appear to be the case for the online reference electrode. We don't find any significant differences for the other measures that we looked at. However, the pattern is trending in the same way. So in terms of our final conclusions and our user recommendations just based on our experience with the product. The modified net with taller pedestals does perform better overall than the short nets in this sample. This appears to be particularly true for infants with hair that was greater than 1 centimeter in length when we measured it. We do recommend the use of this widely available leave-in conditioner. For us, we used the Shea Moisture Jamaican Black Castor Oil Strengthen and Restore Leave-In Conditioner. The use of this product really helps to reduce tangling during net placement and removal and provides additional moisture. And this just really seems to help for net placement and removal, especially for infant participants, based on our experience. And this detangling and moisturizing aspect of adding conditioner is also made it easier for electrodes to sit flush against the scalp for recording. The tall pedestal electrodes are more likely when you're placing the net to be tilted on their side instead of immediately sitting upright and flush on the scalp. So we would recommend an extra pair of hands from a researcher on the study, or in the case of infants and toddlers, from the participant's caregiver to sort of help flip those electrodes right side up. And that will be helpful in reducing the time it takes to place these nets. And finally, in the course of our testing, we did size down the tall pedestal nets by a centimeter, which I believe is now reflected in the sizing that Trey was talking about earlier. And yeah, so those are our recommendations based on our testing. We did only test with the infant caps in this sample, so those are the only results that we're sort of talking about today. But I'm happy to answer any questions.
Thanks so much.
Sorry, Trey.
Go ahead. Go ahead, John.
McCormick, that was fantastic, and Trey as well for the introduction of that. I think this is fantastic, as it brings more diversity into the neuroscience research space, which can only lead to better results and better understanding for all populations. At the moment, I only have one question. It's kind of a TMS EEG question related to the taller pedicle. If the electrodes are 9.3 centimeters, how can you use them for TMS EEG, as the TMS amplitude will be lower on the scalp? Um, I don't know if Trey wants to try that, or Dr. McCormick, but
So the 9.3 millimeter electrode, that's the tall version of the sensor net. And so we wouldn't normally recommend the tall net for TMS EEG. As we were showing in some of the data, you can still use the shorter standard nets that are at the 6.5 millimeter size to get you a little closer to the scalp. But with that 6.5 millimeter electrode, we did still find that you had to increase the power from the TMS device by about 10% to accommodate for that additional distance. So for, I think, most populations, and John can correct me if I'm wrong on this, but for most populations that's doable. But there's going to be certain circumstances where that might not be possible. And so uh, that's when you might need to use the microcell, or think about options for working with that population.
I also think that TMS is only one little part of using this net. This net is going to be used for so many other studies that the advantages outweigh the fact that it may not be as great for TMS as a shorter pedestal.
Yeah, and I think as Sarah's data shows, there's definitely a benefit, and I think that if you're working with infants and sensitive populations, and you have these concerns about being able to get your participants through a challenging protocol where you need enough trials and you really need good data quality, and that's really your main focus, then that's the tall pedestal, I think, or tall net actually gives you that additional kind of quality to be able to get through and get the outcome measures that you need. Whereas if you were doing TMS EEG, you really have to think about how you're going to get the best TMS EEG signal. And we have the two options that we discussed today. So hopefully that helps. And we can kind of talk about anything else, any other questions offline.
Yeah, we've got a couple more quick questions here. Would you recommend the leave-in conditioner for adults also? And what was the name of the product that was used again, just to get it back out there?
So I have never done any testing with adults. So disclaimer that yes, I'm very much an infant researcher, but I think I would recommend the use of the leave-in conditioner for adults as well. I think it would work just as well. And the particular product we used was Shea Moisture Jamaican Black Castor Oil Strengthen and Restore Leave-In Conditioner. That's the full name. That's the one we used most commonly, although towards the end of data collection with, this is a longitudinal study, we did switch to the Cantu Shea Butter Leave-In Conditioning Repair Cream. And these will be included, these names will be included in the preprint we're releasing in a couple weeks as well. But it was just more accessible and easier to get in Cape Town in particular, which was the only reason for sort of switching brands. But yeah, definitely definitely recommend for infants, and I imagine it would work very well for adults as well.
Another quick question here. This is probably more directed towards Trey. Can existing bells and sponges on existing cats be replaced, or must a whole new net be purchased?
So yeah, unfortunately, it is going to be a new purchase. We would discourage replacing all of the pedestals and sponges on an existing sensor net, just because it is the majority of electrodes on the net. And when you remove the sponges and do all of that, you do run the risk of damaging electrodes. So I think, the best approach is really to think about this in terms of, you know, net purchases and how it might factor into your kind of next round of purchases.
Okay, thanks, Trey. And the last question I have is, did any of the participants comment on comfort compared to the shorter pedestals?
Well, they don't comment verbally, mostly because they can't talk yet. But we did not notice any differences in fussiness, either sort of anecdotally during data collection, or any differences in our data analysis, like systematically as a result of that. So I wouldn't say that they're any more or less comfortable than the short pedestals.
Great. On that note, I think that's all the questions we've had. Thank you, Dr. McCormick. Thank you to Trey as well. And I see Ronnie's back on the screen. We'll let her say goodbye.
No, I just wanted to give everyone a massive shout out for joining us today, and special thanks to Doctors McCormick and Avery. This was an amazing session. I love that we just keep adding things into our dense array system to help analyze and take neuroscience further. Everyone have a great rest